Engineering Design Hazard and Operability Studies HAZOP, embedding systematic risk identification and operability assurance into process design and engineering review. HAZOP Guidelines, a structured approach to uncovering hidden hazards and operational weaknesses. The hazard and operability HAZOP technique represents one of the most structured, disciplined, and widely accepted methodologies for proactively identifying design-related hazards and operability issues in complex process systems. Rooted in engineering rigor and driven by multidisciplinary insight, HAZOP offers far more than checklist compliance. It enables organizations to explore what could go wrong in a formal, auditable, and technically inclusive manner. HAZOP is not merely an exercise in hazard recognition. It is a creative, guideword-driven exploration of deviation, intent, and consequence. It thrives on structured imagination, peer challenge, and a shared commitment to anticipate the unpredictable before it manifests as failure. What is a HAZOP? HAZOP is a systematic qualitative study technique applied to process design drawings, primarily process and instrumentation diagrams, P&IDs, to identify hazards, potential deviations from design intent that may result in unsafe operating conditions, environmental releases, or personnel exposure. Operability problems, conditions that could compromise plant performance, efficiency, reliability, or maintainability. Through the structured pairing of guide words, e.g. NO, more, reverse, with process parameters, e.g. flow, pressure, temperature, HAZOP drives a disciplined brainstorming of credible deviations. These deviations are then examined for causes, consequences, existing safeguards, and, where needed, recommended corrective actions. Who participates? A successful HAZOP is a team effort. It requires domain specialists with in-depth knowledge of process control, operations, instrumentation, and safety, an independent and skilled chairman who facilitates with structure, impartiality, and technical depth, an experienced secretary to ensure all findings are captured in a traceable, auditable format. Crucially, all members must bring an open, imaginative, and non-hierarchical mindset. HAZOP is about structured curiosity, not positional authority. How is it conducted? The HAZOP process involves dividing the system into manageable process elements, small enough for meaningful analysis, large enough to retain system context, applying combinations of guide words and process parameters to each element to generate deviations, identifying causes for each deviation, both hardware-related, e.g. valve stuck closed, and systemic, e.g. operator error, determining consequences and whether they pose safety or operational concerns, assessing existing safeguards, e.g. relief valves, interlocks, alarms that mitigate the risk, recommending actions where safeguards are inadequate, ambiguous, or absent. This loop continues until all guideword parameter pairs are exhausted for the selected process element, after which the team proceeds to the next element. Where does it apply? HAZOP is ideally suited for new plant designs, typically conducted near the end of detailed engineering when P&IDs are nearly finalized. Modifications to existing systems, where new existing interactions may introduce fresh risks. Existing facilities, especially where legacy systems may no longer align with current standards or operational practices. It is most effective when applied to continuous processes, though, with some adaptation, it can be applied to batch operations as well. When should it be performed? Timing is critical. A preliminary HAZOP may be conducted on process flow diagrams, PFDs, during basic engineering to catch early-stage hazards. A full HAZOP is typically scheduled late in detailed design, when P&IDs are mature but still flexible enough for recommendations to be implemented without major cost or delay. Why is it essential? HAZOP is not optional. It is fundamental to responsible design. Its value lies in uncovering hazards not visible through design review or simulation, bringing cross-disciplinary insight to bear on complex system behavior, avoiding costly rework or post-commissioning modifications, supporting safety case development, regulatory compliance, and emergency planning, creating an enduring knowledge base for operational procedures, incident investigation, and future expansion. It is also a cultural lever. Well-executed HAZOPs foster collaboration, ownership, and proactive risk thinking across the engineering and operations spectrum. What does a HAZOP deliver? Auditable records of every deviation, cause, safeguard, and recommended action. Annotated master P&IDs indicating process elements studied. A HAZOP report detailing terms of reference, team composition, key findings, and log sheets. Follow-up tracking of recommendations and their closeout through project or operations action plans. The principle behind the practice. A HAZOP is only as strong as its weakest link, whether that is inattentive participation, vague scope, or poor documentation. To achieve meaningful outcomes, every step must be structured, inclusive, and fully documented. More than a technical tool, HAZOP is a mindset, an institutional practice that embeds foresight into design and ensures that safety, reliability, and operability are not left to chance, embedding systematic risk identification and operability assurance into process design and engineering review. Understanding HAZOP, intent, origins, and value. HAZOP began as a pioneering risk analysis tool developed in the chemical industry during the 1960s, born from the realization that complex process systems could fail in unexpected ways despite technically sound designs. It introduced a transformative concept in engineering safety, that hazards and operational difficulties are often embedded in the assumptions, omissions, and cross-discipline blind spots within the design itself. The intent of HAZOP is both simple and profound: to identify potential deviations from design intent and assess whether those deviations could lead to unsafe or unworkable conditions. It is not about predicting failures with absolute precision, but about proactively exploring the boundaries of what could go wrong and where safeguards may be missing, insufficient, or misunderstood. Unlike audits or inspections, which rely on checklists and predefined criteria, HAZOP is a systematic but imaginative exploration of risk. It thrives on structured inquiry, using guidewords and parameters to probe for deviations in every section of a process. This format forces engineers to challenge assumptions, uncover hidden interdependencies, and visualize how a seemingly minor failure could escalate. The origin of HAZOP lies in the realization that process drawings, especially PNIDs, encode thousands of decisions about flow, pressure, chemical interaction, control systems, and equipment behavior. When these drawings are reviewed line by line, parameter by parameter, with the right team and framework, they reveal vulnerabilities that may not surface until late in commissioning or after an incident. HAZOP adds value by creating a shared understanding of design intent across disciplines, minimizing gaps and misinterpretations, generating practical risk reduction measures that are embedded early enough in the project lifecycle to be cost-effective, enhancing plant reliability and performance by surfacing operability bottlenecks before startup, providing a solid basis for safety case development, environmental compliance, and emergency response planning, strengthening organizational culture by reinforcing the expectation that every risk is worth exploring and every voice in the room can contribute to safer outcomes. At its core, HAZOP is not just about processes. It is about how people think about processes. Its structured format ensures consistency, while its open-ended nature invites curiosity and creative problem solving. It protects not just against known risks, but against unspoken ones, those buried in assumptions or hidden in the complexity of the design. The enduring value of HAZOP lies in its unique ability to bridge engineering precision with operational foresight. It ensures that what is designed to work in theory will also be safe, stable, and manageable in the real world, where conditions change, people intervene, and consequences matter. Embedding systematic risk identification and operability assurance into process design and engineering review. Building the right team, roles, and behavioral skills. The success of a HAZOP study depends not only on process knowledge and technical accuracy, but on team dynamics, behavioral discipline, and role clarity. HAZOP is a team-driven technique that relies on diverse perspectives and structured engagement, meaning the makeup, conduct, and collaboration of the group are as critical as the method itself. At its best, a HAZOP team becomes a high-functioning risk identification unit, capable of thinking creatively, listening constructively, and challenging assumptions without ego. This only happens when roles are clearly defined and behavioral expectations are understood and upheld throughout the study. Key roles within the HAZOP team. Chairman, team leader, the single most critical role in the study. The chairman leads with authority, neutrality, and clarity of purpose. They are responsible for guiding the team through each process element and maintaining structured progression, managing time, energy, and focus across sessions, drawing out insights from quiet members while managing dominant voices, ensuring technical rigor without allowing the study to descend into excessive detail or off-topic discussions, making sure all discussions are captured accurately and actions are formulated clearly. A good chairman is part facilitator, part engineer, and part strategist. Secretary, scribe. A highly focused and methodical role. The secretary is responsible for recording every credible deviation, cause, consequence, safeguard, and recommendation in real time, ensuring consistency of terminology and clarity of entries, marking up master P&IDs to reflect elements reviewed, maintaining attendance records, document lists, and supporting notes. Their role preserves the auditability and traceability of the study and is crucial to post-study reporting. Process design engineer brings in-depth knowledge of the system under review, provides context for design intent, operating modes, and process control logic. Control and instrumentation engineer offers insight into logic, interlocks, trip settings, alarms, and potential failure modes in automated systems. Operations specialist, a key contributor who understands how systems behave in real-world conditions under startup, shutdown, maintenance, or upset scenarios. Project engineer, systems engineer offers cross-functional integration knowledge, ensuring alignment with project scope, standards, and interface points. Safety, HSE specialist, interprets hazards in relation to personnel safety, environmental exposure, and regulatory frameworks, brings structured safety thinking to the room. Other discipline experts as needed. Electrical, mechanical, piping, or vendor specialists may be invited to address specific concerns or contribute deep domain expertise during select sessions. Behavioral skills that define an effective HAZOP team, structured thinking, ability to stay within the method and focus on one deviation at a time without jumping ahead or drifting into solution space too soon. Constructive challenge. Team members must be encouraged to ask, "What if?" without fear of being wrong. Psychological safety is essential. Active listening. Each participant must listen to others' inputs attentively and build upon them, especially when evaluating causes and consequences. Open-mindedness. Creativity and curiosity must override defensiveness. Assumptions should be probed, not protected. Concise communication. Clarity and brevity in technical discussions help prevent misinterpretation and reduce fatigue. Respect for structure. Discipline in following guide words, logging decisions, and adhering to the agenda sustains the productivity of the team. Sustaining team energy and engagement. Limit study sessions to manageable blocks, ideally 2 3-hour sessions per day. Maintain consistent team composition to preserve continuity and group rhythm. Rotate seating or assign review leads to keep energy and involvement high. Use visuals, models, or simulations where possible to aid understanding. Encourage regular breaks and light moments. HAZOPs are intense by nature. Ultimately, a well-composed and behaviorally disciplined HAZOP team becomes more than the sum of its parts. It transforms a technical procedure into a shared mission, one that defends against the unknown by asking the right questions at the right time with the right people. Embedding systematic risk identification and operability assurance into process design and engineering review. Process mechanics, from parameters to recommendations. At the heart of the HAZOP methodology lies a structured and repeatable process, a disciplined mechanism for dissecting complex systems into manageable parts, exploring how deviations from design intent could arise, and determining whether those deviations pose unacceptable risks to safety or operability. This section demystifies the inner workings of that process, how guide words, process parameters, and team insight are converted into tangible recommendations. Step 1, define the process element. Each HAZOP study begins with the selection of a process element, a discrete section of the system, e.g. a pump suction line, vessel inlet, or heat exchanger loop. The element must be small enough that deviations are meaningful and not generalized, large enough to preserve context and efficiency during the study. Each element is reviewed one at a time, ensuring nothing is overlooked and the scope is traceable. Step 2. Apply guide words and process parameters. Guide words are conditional triggers, words like no, more, less, reverse, misdirected, that are applied to process parameters such as flow, pressure, temperature, or composition. When combined, they produce a set of hypothetical deviations from design intent. Examples: no flow, complete blockage or pump failure, more pressure, overpressure due to control valve malfunction, less temperature, heat exchanger failure or utility loss, reverse flow, check valve failure or pressure reversal. These combinations act as structured prompts, forcing the team to imagine failures they may otherwise never consider. Step 3. Identify credible causes. For each deviation, the team brainstorms plausible, realistic causes. The focus is on credibility, not exhaustive listing. Examples of causes: valve incorrectly closed, instrument failure or miscalibration, operator error or procedural gap, equipment fouling or wear, utilities lost, e.g. cooling water, nitrogen, air. Caution is exercised to avoid speculation or highly improbable failure chains. If a cause is not credible, it is discarded. If it is, it must be recorded. Step 4. Evaluate consequences. The team then explores the consequences of each deviation if it were to occur. Considerations include equipment damage, e.g. cavitation, rupture, overheating, process disruption, e.g. loss of control, off-spec product, personnel hazard, e.g. toxic release, fire explosion, environmental impact, e.g. spill, venting, discharge. This is where the team's collective experience and insight truly matter, understanding not just what could happen, but what is likely to follow, how fast, and how far. Step 5. Review existing safeguards. Each identified consequence is examined in light of existing protections. These may include relief valves, rupture discs, flame arresters, alarms, trips, interlocks, permissives, manual procedures or administrative controls, equipment design margins or redundancy. The team assesses whether these safeguards are effective, appropriately located, and adequately designed. If a deviation is well covered, the study moves on. If not, it proceeds to the next step. Step 6. Recommend actions. If a deviation has credible consequences and insufficient safeguards, the team formulates recommendations to improve safety or operability. These fall into 4 categories. 1. Hardware changes, e.g. add a relief valve, move a temperature sensor, upgrade material specs. 2. Procedural controls, e.g. new operating instructions, revised startup sequence, maintenance checks. 3. Further study, e.g. seal assessment, quantitative risk analysis, QRA, flare load calculations. 4. Project feedback. For issues beyond the HAZOP team's scope or that require strategic decisions, recommendations must be clear, actionable, and justified. They are not solutions. They are triggers for change, handed back to the project or operations team for resolution. Step 7. Document findings. Every credible deviation and its associated cause, consequence, safeguard, and recommendation is recorded on a standardized HAZOP log sheet. This log becomes the core of the HAZOP report and ensures auditability for future reviews and investigations, traceability of team thought process and rationale, action tracking and closure by responsible parties. Step 8. Move to next process element. Once all guideword parameter combinations are exhausted for a given process element, the team proceeds to the next, repeating the structured cycle until the entire system has been studied. This rigorous yet flexible method transforms static drawings into dynamic risk landscapes, inviting teams to challenge assumptions, anticipate consequences, and engineer resilience before the system is ever built or modified. In the mechanics of the HAZOP process, every question asked is a defense earned. Embedding systematic risk identification and operability assurance into process design and engineering review, common pitfalls and best practices. While the HAZOP method is inherently structured and systematic, its effectiveness depends heavily on how it is applied. Even well-planned studies can fall short if subtle but critical missteps occur during preparation, execution, or follow-up. Recognizing common pitfalls and embedding best practices to counteract them is essential to ensuring the HAZOP becomes a value-generating process rather than a box-ticking formality. Pitfall 1. Poorly defined scope or terms of reference. A HAZOP study without clear boundaries or objectives can quickly derail into confusion or superficiality. Best practice: define a formal scope and terms of reference in writing, detailing what will be studied, what is excluded, and how vendor packages, future provisions, or partial P&IDs will be handled. Align expectations between the HAZOP chairman, the client, and the project team from the outset. Pitfall 2. Incomplete or inaccurate documentation. Outdated or incomplete P&IDs, missing data sheets, or poorly prepared drawings compromise the foundation of the entire study. Best practice: ensure that all documents are current, approved, and at the correct revision. Include supporting documents like cause and effect charts, shutdown philosophies, and vendor data where relevant. Allocate time for the HAZOP team to become familiar with the documents before the study begins. Pitfall 3. Inadequate team composition. Missing expertise, overrepresentation of a single discipline, or frequent rotation of team members dilutes the depth and continuity of analysis. Best practice: assemble a balanced, multidisciplinary team with the right mix of process, control, operations, maintenance, and HSE expertise. Maintain consistency in team attendance across sessions. Bring in specialists as needed, but keep the core group stable to preserve momentum and shared understanding. Pitfall 4. Dominance or passivity in team dynamics. When certain members dominate the conversation or others remain silent, valuable insights are lost. Best practice: the chairman must foster inclusive participation, use directed questions, rotate element leads, and encourage even junior or soft-spoken members to contribute. Psychological safety is key. Every deviation considered helps sharpen the overall analysis. Pitfall 5. Overloading the log sheet. Recording speculative or non-credible causes can lead to excessive documentation, diluting focus, and overwhelming follow-up teams. Best practice: record only credible causes, consequences, and actions. Encourage open brainstorming, but apply discipline in filtering what makes it to the log sheet. Use language that is concise, unambiguous, and reflects consensus. Pitfall 6. Focusing only on safety hazards. HAZOP is often mistaken as a purely safety-focused exercise, neglecting issues that affect plant operability, maintainability, and reliability. Best practice: actively explore operability problems, such as startup complications, maintenance conflicts, or nuisance trips. View HAZOP as a performance assurance tool, not just a safety gate. Pitfall 7. Rushing through process elements. Teams may attempt to power through sessions, leading to cognitive fatigue and superficial analysis. Best practice: plan realistic session lengths, ideally 2 3-hour blocks per day, and take regular breaks. Monitor concentration levels and adjust pacing. For complex systems, quality matters more than quantity of pages covered. Pitfall 8. Weak or untracked follow-up. Even the most insightful recommendations are worthless if they are not implemented, validated, and closed out. Best practice: assign a single point of responsibility to track actions, maintain an action status register, and report closure progress. Consider reconvening part of the HAZOP team to review critical follow-ups and confirm adequacy of responses. Pitfall 9. Treating HAZOP as a one-time event. Some organizations view HAZOP as a task to be completed during design and then archived. Best practice: integrate HAZOP findings into the life cycle of the plant. Reference them in operating procedures, training, incident reviews, and future modifications. Maintain HAZOP reports as live documents that inform both daily operations and long-term strategy. HAZOP is not immune to failure, but its strength lies in its structure. When that structure is applied with discipline, supported by engaged minds and sound documentation, it becomes a powerful lens through which risk is revealed, foresight is practiced, and engineering becomes proactive rather than reactive. Avoiding these pitfalls and embracing best practices elevates HAZOP from a technical review to a foundational safeguard of process safety and operational excellence. Embedding systematic risk identification and operability assurance into process design and engineering review. Beyond the study. How to drive real-world action. A well-executed HAZOP study is only half the journey. The true value of the process is unlocked after the last log sheet is signed, when recommendations are acted upon, systems are updated, and lessons are embedded across the organization. Without structured follow-through, even the most insightful findings remain static, valuable in theory but disconnected from practice. Driving real-world action from a HAZOP study demands ownership, traceability, accountability, and closure. It requires shifting from what we found to what we will do about it, and ensuring the changes are implemented in a way that is technically sound, timely, and aligned with operational goals. 1. Formalize recommendations into trackable actions. Once the study concludes, all recommendations should be logged into an action tracking system or project database, assigned unique action IDs tied to their source PNID and log sheet entry, categorized by urgency, complexity, and type, e.g. design change, procedural update, further study. Avoid vague or generalized entries. Each action must be clear, assignable, and measurable. 2. Assign clear ownership and deadlines. Every recommendation must have a single accountable owner, typically from engineering, operations, HSE, or project management, a due date that reflects the priority and complexity of the action, defined expectations for deliverables, e.g., revised drawing, new procedure, completed analysis. Ambiguity leads to inaction. Clarity enables progress. Tab 3. Engage technical authorities in evaluation. Not all recommendations require implementation as is. Some may be addressed through alternative controls or procedural safeguards, deemed non-credible upon deeper analysis, deferred with justifiable reasoning based on cost-benefit or technical constraints. To support this, technical authorities must evaluate each action and document their acceptance, modification, or rejection with full traceability. Reconnect with the HAZOP team if needed. For complex or safety-critical actions, reconvening the HAZOP team or a subset can validate the proposed resolution, confirm whether residual risk remains acceptable, strengthen the design assurance process. This HAZOP review loop builds confidence in how recommendations are closed. Integrate changes into design and operations actions are not complete until they are embedded into the plant's technical and operational ecosystem. This means updating PNIDs, loop diagrams, data sheets, and cause and effect charts. Revising operating and maintenance procedures. Adjusting control logic, interlocks, and alarms in DCS ESD systems. Training operators and maintainers on new risks or procedures. Closure is not just a signature, it's demonstrated readiness in the field. Number 6. Monitor implementation through structured follow-up. Establish a HAZOP action status register that is regularly updated and reviewed in project or safety meetings. Auditable by internal teams or external regulators. Used to escalate overdue or high-impact items. Ownership must persist until completion, not fade with project transitions. 7. Capture lessons learned for future studies. Each HAZOP study generates insights beyond the immediate design. These lessons should be documented in post-study reviews or closeout reports, shared across projects, disciplines, and contractors, used to inform design standards, checklists, and future HAZOP preparation. A single missed deviation or recurring issue across studies can reveal systemic gaps in assumptions, design practices, or process safety culture. 8. Reinforce a culture of action-oriented risk management. Ultimately, HAZOP is not a static deliverable. It is a behavioral signal. How an organization responds to its findings reflects its commitment to anticipating rather than reacting to risk, valuing cross-disciplinary input and procedural discipline, protecting people, assets, and the environment not just in design, but in day-to-day operation. When real-world action flows naturally from HAZOP output, it transforms from a compliance tool into a strategic safeguard, a living system that enhances not only what we build, but how confidently we operate it.